All right, my little small things. I believe I am finally recording. What's up? It's nice to see you, Jocelyn. Okay, so do you have homework or stuff to work on?
Yeah.
Go for it. All right, my little ones. I'm so excited to see each and every one of you. Welcome to class. You've got your capture question up on the board. It says, do you think that our planet always looked as it does now? Please get out your notebook and write it down. Please get out your notebook and write it down. Then I want you to explain your reasoning. And what I mean by does it look or has it always looked the way it does now? I mean, if we look at this model of the planet Earth, you can see that we've got very distinct land masses, right? We've got very distinct land masses. And I want to know, have these land masses always looked this way and always been in this position? Have they always looked like this? Has the Earth always looked like this? Has the Earth's land masses always been in this position? I am so excited that you were on time. Thank you very much. I appreciate that about you. So I'm going to go ahead and put this model here. If my wonderful student who just got into class, if you could please get out your notebook and write down your question of the day. If you'll notice, you're also going to need your Chromebooks today. So while you are waiting for us to share out, you can get out your Chromebook and set it up. Today is festive sweater day.
Can I expect this so I can?
Absolutely.
Wait,
You'll notice my festive sweater. Wait, what?
are we doing the quiz today?
Say again?
Are we doing the quiz today? Okay.
We're not going to have our quiz today. So the answer to the question, do you think that our planet has always looked as it does now? Give me a hands up in the air if you think, yeah, it's always the way it's been, just the way we see it today. It's never changed. Oh, give me a hands up in the air if you think, no, this has changed over time. I would agree with you. My hand's right up there too, but that's the easy thing, right? It's super easy for us to go ahead and say no, the Earth has changed over, that's not how I spell changed over time. So now my question is, explain why you said no. Thank you very much for waiting, Kyle. Explain, why do you think that the Earth has changed over time? Or what was your reasoning for saying no?
Because due to the way our continents came together, it formed it was like a puzzle where they all fit together perfectly.
Do you remember what that was?
The tectonic.
But do you remember what the supercontinent was called?
No.
Help him out. Yeah, Pangea. So I heard you say lots of things there. I heard you say the way that the continents were moving. I heard you say something about they were all together like a jigsaw puzzle. And then I heard you say something about plate tectonics. So what I'm hearing you say is that the land masses have moved due to plate tectonics. At this particular point in time, do you know why that happens? It's okay if you say no, we've not talked about it yet.
Isn't something reaction happening in the Earth's core?
There is something happening inside the Earth. It's not quite in the Earth's core, it's in the mantle. There are convection currents that are moving. And remember when I said that those currents move about as fast as your fingernails grow. And because of that magma moving is literally pushing the land away or pulling the land together. And it happens super, super slow, like your fingernails growing. Can we feel the land moving beneath us at all? Can you think of any time when we might? Kai? Earthquakes! And earthquakes happen because if you picture my hands as being two like giant slabs of the lithosphere, right? And plate tectonics is the movement of those slabs. they slide by each other, no problem. But those slabs of land, that rock is not smooth. And so it gets stuck. And so if that land is trying to move inches a year and it gets stuck, well, this part of the land and this part of the land is still moving, but this at the boundary is locked in place. And all of a sudden, if rock breaks and it moves really quickly to catch up with the rest of the land, that's an earthquake. And sometimes it can be years and years and years and years that it's stuck in place. And so you have lots of movement, sometimes meters of movement all at once when the land moves. Can you think of any other reason that the land might not look the same anymore without plate tectonics? Mason.
The evolution of plants.
Explain that to me, Mason.
As climate changes, plants adapt to their surroundings and change forms.
But how is that changing the land?
You mean like the ground?
Yeah, the ground.
Same as like the.
Oh, you're saying if we have more plants, it's not going to look the same.
Yeah.
I understand what you're saying. Yeah. I'm talking about the actual land itself. Can you think about any other ways that the land itself is changed? What other factors on our planet could possibly change the land? Jackson. Are you with me?
Yeah.
What other factors on our planet could possibly affect or alter the land?
Natural events
Like what?
like thunderstorms.
Thunderstorms. So we've got rain, we've got water. We've got water erosion that could possibly change the land. So let's go ahead and add that too. That was part of our reading that we did. We had those other factors like wind, ice, water. So water can erode the land. Erosion means to move it around. So you can have land masses being moved because of plate tectonics, but you can have also factors like water that can erode the land. Can you imagine anything from outside of our world that might affect the land, that might change the landscape? What do you think, Mason?
Asteroids.
Yeah, what if meteorites come in? We could have meteorites coming in from outer space. That can definitely change the land. So there's lots of different ways that we can have the land change. And we're going to be talking about some of these as we move through the unit. But today, we're really going to be focusing on this first one that Kyle brought us to, this idea of plate tectonics. So in your unit packet, could you please open up your packet and find where it says the moving lithosphere? The moving lithosphere, because when we first started this unit, we started talking about this idea that the Earth has layers, right? We read that article and we talked about that the Earth has different layers. Then we took these notes and we said, hey, these notes show what the layers are. Now we're going to look at that first two layers, which is the lithosphere. That's the crust in the upper part of the mantle. And we're going to look at how that lithosphere is moving over time. So it says the Earth's familiar continents, arranged in the dependable configuration that you know and love, didn't always look the way that it does now. Its land masses, once locked together in supercontinents, like Pangea, have cracked and broken and slid away from each other, repeatedly come together again and again and formed mountains over the course of our planet's 4.5 billion year history. We've got some steps. The first thing is we got to click on this link. You can't click on that link because it's a piece of paper. So you need to either open up this document electronically or go to Canvas. And on Canvas, you will see that we have, I want to hide this. I want to go to this. On Canvas on today, which is Tuesday the 15th, you've got the electronic version of the document, which you could open and click on the link, or you can just click on this interactive map link right here. It should bring up what the Earth looked like 750 million years ago. Can you please just raise your hand and let me know when you're here? Fabulous. Fabulous. Peyton, do you know where to go?
Yep.
Good. Thank you, Jonah. Thank you, Kai. Thank you, Haley. Thank you, Mason. Jackson, you said you're good? So again, a quick way to do it, just go ahead and go to Canvas, click on this little link, and you'll be right there. And then we see what the Earth looked like 750 million years ago. If you look at number 2 on your piece of paper, it says we're going to enter in a city name that we live in so we can show it on the map. So I'm going to show you up here on the big board. If you look at this little area right here, could you please type in where you live? I'm going to type North Liberty, Iowa. You can type in Coralville, you can type in Iowa City, whatever you'd like. And then we've got a little pin that shows us 750 million years ago where North Liberty, Iowa was located on the planet. Looks nothing like it does today. Could you then please go over here to where it says display options and then click and get rid of those clouds. We want to see them much better. Click on rotate globe. And then could you please show the equator? So you should have rotate globe and show equator. And then when you're finished, click done. Now we see it better because we don't have the clouds in the way. Notice I can see the equator. I'm going to go ahead and tilt my planet down so that the equator is where I'm used to it, right there in the middle. At this point, we're pretty close to the equator. So 750 million years ago, I'm assuming that our location was probably much warmer than it is today. We probably did not have snow on the ground. So this was the cryogenian period. Cryo meaning ice and snow. Glaciers may have covered the entire planet during the greatest ice age ever known on Earth. It was called snowball Earth by scientists. New types of life, such as red and green algae, appeared during this time period. So if we look down below on our piece of paper, you'll notice that I already filled that in along with the time period that we're looking at. So that's what we're doing. Let's go ahead and go to 6 million years ago and find out what that time period was called. 600 million years ago, click on it, and this is the Ediacaran period. So we're going to write that down on our piece of paper. Ediacaran period. Okay, we're going to take some very basic little notes here about what it is that was going on during that time period. So during that time period, it looks like life was evolving in the sea and multicellular life was beginning. So those are the two big things there. Life begins in the sea. No, life evolving in sea and multicellular life begins. Now, guess who else is multicellular life? You're multicellular life. So this is a very important part for our history. If we could go back ancestry.com far enough, we'd find our ancestors 600 million years ago. Let's go ahead and check out 540 million years ago and see what was going on there. Oh, what do we notice about where North Liberty, Iowa was? Look how far away we are now from the equator. We're way down at the pole. I'm guessing it was probably very, very cold during this time period. 540. All right, now look, we can see where the United States is supposed to be. We can see Iowa. It looks like we're on the edge of a giant lake. This is the early Cambrian. There was a mass extinction that's just taken place. Afterwards, the fossil record shows dramatic expansion of animal life in the sea, known as the Cambrian explosion. So if we go back, let's go ahead and label this as the Cambrian. Cambrian period. And in the Cambrian period, one thing we need to note was that there was a mass extinction. After the mass extinction, then there was an explosion of life. There was what's called the Cambrian was it expansion or explosion? I think explosion. This was an expansion of life. So it seems like we're going to see a pattern evolve where every time there's an extinction, there then becomes this massive opportunity for life to fill that gap. All right, let's see what else happened that might be important during that time period. Animals began to evolve shells and exoskeletons. Let's go ahead and put that down. So at this time period, now we have shells and exoskeletons. What's an exoskeleton? Do we have one? We don't have exoskeleton. Exo means exit, on the outside. Where's our skeleton? Internal. Exoskeleton would be like a cockroach. You step on the cockroach and it goes crunch. That's because we're squishing its outside. Exoskeleton would also be lobster. Has anybody ever had lobster? Lobster tastes good. Lobster is basically just like an insect that lives in the sea, right? Dip it in butter, yum yum. I wonder if a cockroach would taste good dipped in butter then. So shells and exoskeletons, that's a big deal because now the squishy things that we're living, now they've got more protection. Let's go ahead and check out 400 million years ago and see where we are. We are there. 400 million years ago. We are now, if I move this in an area where I can see, I'm kind of halfway between, I'm more closer to the poles, I think, than I am the equator. This is the Devonian period. Does the Devonian sound familiar to anybody? Did anybody take a field trip when you were a kid in the area and go to the Devonian Fossil Gorge? The Devonian Fossil Gorge is a place that enables us to see this time period in the world. On this, we have life on land becomes more complex. So we're going to start by writing that. Life on land becomes complex. Now, let's go ahead and list why it becomes complex. What in the world was happening so that life became complex? It looks like plants are developing. We have insects developing. Fish have fins. So I need to write those down so I'll forget. So we've got plants, insects, fish with fins, and eventually those fins are going to become what they can walk with on land. What? Fish can't walk, but when you talk about like how things evolve over time, those species will then create new species where those fins will then become kind of like limbs. The first vertebrates walk on land. That's a big darn deal during this time period. So we're going to write that down. First vertebrates walk on land. That's huge because we are vertebrates. First vertebrates walk on land. Oops. Great, so now let's go ahead and check out what happened 300 million years ago. Was it 300 million years or? Late Carboniferous. So this is the Carboniferous. Does anybody know anything about the Carboniferous period? I have this fossil from that time period. What do you think this is a fossil image of? What's it look like? Ah, good. That's what a fossil is. What do you think, Kyle?
Kind of like scales.
Yeah, scales from what though? Not an alligator. There wasn't alligators back then. But this kind of an organism did have these kinds of scales. You can see the outer layer and then the inner layer. This is tree bark. This is a very different kind of tree bark. It's scaly. It's different. The trees that were around during the Carboniferous were very different than the trees that we have today. Okay, this is from the Carboniferous period. And so late Carboniferous, plants have developed all over the world. So it is warm here. And if you think about it, think about the whole world as a giant forest. So we have huge trees. Plants grow, and we don't even call them trees at this point. They're just plants. So this is the carbon, as in carbon, lots of carbon-based life forms. Carboniferous, period. And you have large amounts of plants. And they're large plants. Large plants cover the world. And because of these plants, guess what increases in the atmosphere? Yes, atmospheric oxygen. Actually, carbon reduces because all the carbon comes out of the atmosphere and gets locked in the plants. So the carbon dioxide levels drop and the atmospheric levels of oxygen rise up. And because of that, we have giant insects. Because insects have what's called book lungs. These creatures evolved from creatures that came out of the ocean, and the ocean creatures have gills. So book lungs are a lot like gills, but they take the oxygen in directly from the atmosphere. And because there's so much oxygen, it enables the insects to get huge because they can be supported with the amount of readily available oxygen. Imagine a centipede as long as these two tables put together, all of a sudden coming through that door and making its way towards Lincoln. A huge centipede. That's how large these insects were. Insects could never get that big now because we don't have the amount of oxygen available to sustain them. Also, we are able to find evidence of this oxygen in our rock records. Can you think of anything in rocks that might turn red when exposed to oxygen? Really think about this. Huh?
Water.
What can you think about what might turn red that's in rocks that when exposed to oxygen, it might turn red? What do you think?
Isn't it iron?
It is iron. So iron rusts when it's exposed to oxygen. So we have records of when there was so much oxygen pumping out into the atmosphere because we see so many layers of rocks that have rusted because of it. 280 million years ago. Let's go ahead and see what was happening then, shall we? All right, there we are. We're really close to the equator now. I'm guessing it was very warm. It was called the Permian period. Come on, Permian. So this was the Permian period. When I was in a class in college, I had to remember, like memorize all the different periods and epochs and eras and All right, so what happened here? Supercontinent Pangea that Kyle and Mason were talking about. So let's go ahead and say supercontinent Pangea happened at this particular time. Extreme conditions such as polar ice caps and deserts limited the extent of plant life. We don't need to write that down. There were amphibians and there were reptiles at this point, and oceans were teeming with life. Look at how different the world looked. Do you see all these big bumps? These are mountain chains that were created when land smushed together. You can see a giant chain kind of forming through here. These are the Appalachian Mountains where I grew up. You can have the Appalachian Mountains through here, and it's because when land smushes together, it's called a suture zone. Has anybody ever gotten a cut in your skin and you got sutures, you got stitches? Imagine that, it's sutured together. That's what they call them in geology. All right, so we are going to have amphibians and reptiles here. Amphibians, I don't know how to spell that. Amphibians and reptiles. Let's go 120 million years ago. We're really jumping through now. Ooh, now we are far away from the equator again. Now it's starting to look very familiar to me. This is a planet that I can recognize, except for it looks like Africa and South America are together. This is the Cretaceous period where the world is warm and we have no ice caps. So Cretaceous. We have a warm Earth, no ice. So this would be like a greenhouse environment. Are we in a greenhouse environment now? We're not, because we have ice. We're in what's called an ice house environment. We're in an ice age. And so we're living through an ice age right now because there's ice on the planet. It doesn't feel like it because we're warming. Yep.
So it started with ice, and now at where we're at right now, it has no ice.
Where did it start with ice, sweetie?
As of the
750 million years ago.
ice cap.
Yep. And that was during, but remember, there was more time before that. But at 750 million years ago, we were covered with ice. And then it kind of like the world changed over time. It has gotten warmer. It has gotten cooler. It has gotten warmer. It has gotten cooler. Right now, we are in a cooling period of time on the planet. But that's not happening. We're supposed to be in a cooling period of time, but it's not happening. Okay, let's go ahead and look at what else. Oh, we have large reptiles and small mammals. You are one of those, or your ancestors are one of those small mammals. So large reptiles, small mammals, mammals. I think there's two M's there. Is there two M's in mammals? And then the big thing that you need to know here, which is super important, is flowers began. Flowers are huge. I mean, when flowers come on the scene, you are talking like diversification of plants on a scale that's never been seen. Flowers is all about sex for plants. I mean, you have all of these beautiful flowers and they are attracting all of these pollinators. And then you've got such diversity that comes because of it. You get fruit that comes because of it. You get all of these wonderful things. So flowers on our planet are huge. On the back of your paper, we need to now look for all of the major extinction events. We found the very first one was 540 million years ago during the Cambrian period. So we're going to write that one down. 540 MYA. This was the Cambrian period. And we don't know what the extinction was at that time. We just know things died, as far as what this document is telling us. The next one we have to then search for. So 540 was when we found the first one. If we go to 500, I don't see anything. 470, Ordovician, nothing. This is when we had jawless fishes. So you had fishes that had no bony jaw. Where am I? 470. So we're underwater here. Notice how most of our area is all underwater. So this is late Ordovician, still no complex life on land. A mass extinction's about to take place. So let's look. Okay, during the Silurian period, a mass extinction took place, wiping out nearly half of marine invertebrate species. So Silurian period, I think that was 430 million years ago. Silurian period. And we lost half of the marine invertebrates. That means these are creatures that do not have a spinal column. They have a spinal cord, but no spinal column. So these are like soft, squishy things still. Okay, let's check out what the next one is. 400, still underwater. 370, late Devonian, still underwater. 340, Carboniferous, underwater. 300, plants develop, still underwater. 280, Permian. Nope, we are not underwater anymore. 260, late Permian. The greatest mass extinction in the history is about to take place, driving 90% of the species on our planet extinct. Look, we have another massive continent right here. Extinction of plants reduced the food supply for large herbivore reptiles and removed habitats for insects. Okay, that's bad. Let's go ahead and see what happens in the next. Early Triassic, oxygen levels are significantly lower due to the extinction of many land plants. Okay, many corals went extinct, with reefs taking millions of years to reform. Small ancestors to birds, mammals, and dinosaurs survived. So let's go ahead on our paper and put a Permian slash, so this is going to be Permian slash Triassic. And we're going to say that 90% of all species. And remember, it's all species. It's not species. It's not just, that's not how you spell that. That doesn't look right. It's not just animals. It's animals and plants and corals. And this was from about 260 to about 240 million years ago. Is that right? Or did I miss one? Is that the right time? Seems like I missed one.
260, right? So it's 240.
Did we miss extinction? Right here. A mass extinction harmed marine life. So we missed this one. In the Carboniferous period, there was a mass extinction that harmed life. I thought there was one that happened about every 100 million years. So that one was 300 and, what was it? Carboniferous. This is a C. And we're just going to put marine life. Sorry, I missed that one. About every 100 million years, it seems like there was a extinction event. All right, now let's go past, let's go look at 260. Late Permian, great, okay, we did that one. Let's go look at 220. Middle Triassic, the Earth is recovering from the Permian Triassic extinction. Small dinosaurs begin to appear. Therapsids, archosaurs, we don't care. 200 million years ago, late Triassic, another extinction event is about to happen, resulting in the disappearance of 76% of all terrestrial and marine life species. Okay, greatly reducing surviving populations. All right, so let's go ahead and write that down. Late Triassic. Late Triassic, and I'm so sorry, I don't remember the date, 200 million years ago. And it was 76% of species on the planet. I want to talk about this one with 90% of all the species, or even 76 of the species. I want you to know how special you are. Imagine that this is all life on Earth, all species, right? All species. You're talking bugs, insects, plants, flowers, grass, everything. And all of a sudden there's an extinction event, and I don't know why, but there's something that happens and it brings all of it down to just 10% of the species left. From that, the world repopulates itself. Do you have any idea how lucky you are that you're here? Everything on the planet just about died, except for 10% of the species. And we are part of what that became. That's crazy. And then, what? Another, 60 million years later, that happened again. Everything kind of came down, right? And then it repopulated again. So you get these extinction events, and think about like all of the life that came before us that didn't survive. But we did. I mean, not in our form, but we came from that. Just, it's unbelievable, really. It's just unbelievable. All right, the last extinction event was 66 million years ago. Is that what you were going to say? What time period was it?
I don't know.
Cretaceous. And what happened, man?
Killed the dinosaurs.
Dinosaurs died.
Flying reptiles.
Yeah, dinosaurs died, and why? Yes, there was a giant asteroid. Asteroid is just like a meteorite on steroids, really big. So they think an asteroid killed out the dinosaurs. There's one more that I want you to write down. I want you to write present day. We are in what's called the Anthropocene. That means, has anybody ever heard of the study of anthropology? That's the study of us, human culture. We're part of the next extinction. We're not dying, we're causing the death. So if you look at what I have over here, this shows all of the different extinction events. This is the one that's happening right now. It's the Anthropocene extinction. Because of our human activity, we are wiping out ecosystems, we are destroying biodiversities, and we are making species extinct. Not us, but other species that we said that we share the planet. So you can see the amount of extinction, like the extinction rate, families of species per million years. And look at this. This goes up here. Look how high this one was. This is up here. This is the Devonian. That should maybe look familiar. You find fossils of that in the Devonian fossil gorge. You can see all the different little peaks of different extinction rates. And we're in one right now. How destructive it'll be, we don't know. But we're killing things because of what we're doing. Not we in here, right? But our lifestyle. All right, let's go ahead and look at letter C, please. 750 million years ago, the location of present-day North Liberty, Iowa was on dry land. When did a shallow ocean begin to flood the town? What did we look up? Who has found something like that for me? Because I know some of you have been moving ahead. When did we start to flood? Anyone? Lincoln, did you find it? 540. So if I look at 540 million, it looks like you're right. We just kind of start a little bit, start to flood. So I'll go for that. Is there another one that we're even wetter than that? 500 million. I'm going to go pick 500 because it's a nice even number for me, and the whole state is flooded. So I'm just going to say 500 million. But Lincoln, you keep yours if you feel comfortable with yours. So 500 million years ago. And how long did it last? It went from 500 million years ago to when? 380. Let me go ahead and look. That's all right. Let's check it out. 300, maybe 280, you think? 340? We're still wet on 340. That's okay. 300, still wet. 280? All right, so 280 million years ago, our land started to dry out. So 280 million years ago, how many years then total was it wet? 220 million years, we were underwater. That's a long time to be underwater. We've got like so much bedrock underneath our cities, and it's all limestone, which is old coral. So we are called Coralville because we have just layers and layers of coral created during that time period. The first hominids, the earliest human ancestors, appear on the planet. Lincoln, what'd you find? What? 20 million years ago. 20 million years ago. Oh, this looks really very familiar to me. Everything is separated. It looks like, yep, now North America, or South America rather, and Africa. Hominids emerged from Africa. So that was 20 million years ago, the earliest hominids from Africa. This was the first wave of hominids that came out of Africa. These hominids spread across the world, not the whole world, but like Eurasia and that area. Their ancestors were like Neanderthals. And then we came out in the second wave from Africa. We were a more modern form of hominid. And from that second wave from Africa, you get all of us in this room. Now, that second wave, there is evidence that that second wave did interbreed with species like Neanderthal. There are certain groups of people, depending on where we live, that we have more Neanderthal DNA in us than others. But, you know, I mean, you're all out there, right? You're interbreeding. You're coming across bands of people. You're probably going to have sex at that point. You know, it's all about like survival and trying to make the tribe larger. All right. Do you think that the current formation of the Earth will be the last? What is your reasoning? This is going to be private to you. And then what happened to the movement of your hometown? Did it stay in one location? The easy answer here is no, it did not. But I want you to explain its movement in relation to the equator. When was it closest to the equator? When did it start moving away from the equator? That's what I want you to work on.